Hi guys, welcome to another video of me teaching mathematics. I'm Abhinav. I've done my bachelor's and master's in electrical engineering from IIT KHARAGPUR. And today we are going to discuss this concept, definite integral, as a limit of a sum. So the plan is to understand the concept from the very basics and then solve a question based on this concept. So this is a very important concept for your JEE advanced. So every year you can expect a question from this topic on your advanced exam in the mathematics section. So I'm planning to make a playlist for this topic, and in this video, the first video of the playlist, we are going to discuss the concept and solve a question based on the concept, and in the subsequent videos we'll be solving the past year JEE questions from this particular concept. So let us understand what the concept is all about. So it is definite integral as a limit of a sum. So this is a technique where you convert a summation, basically sigma, into an integral. Alright. So let us say you have a limit. So for example, this is the limit that you have to evaluate. So you convert this limit somehow into an integral. Okay. And the answer to this integral will be the answer to your limit. All right. So you have to somehow manipulate this limit and express this in as a summation of some terms, and then once you get the summation, you have to convert this summation into an integral and solve this particular integral instead of solving this limit directly using the techniques of limits that you have learned. All right. So with that, let us go ahead and understand the concept. Okay. Let us consider we have a function f of x. All right. And if we have to compute, and okay, let us say we have a function f of x, and let's say f of x looks something like this. Here you have a and here you have b, and you have to compute the area under this curve f of x from a to b, this particular area. So generally what do? We find this integral, and the value of this integral will be the area under the curve from a to b. So how did we get to this particular result, f of x dx? So let us understand how the area works. So let us say you have this function f of x, and let us divide this area between a and b into two parts. One part, this is one part, and this is the second part of the area. Okay. So now to find out the area under this curve, let us follow a certain technique. Instead of finding the entire area, so let us make two rectangles. So this is one rectangle and this is one more rectangle. So the idea is to find out the area of this particular rectangle and the area of this particular rectangle, and then sum up those two areas. All right. So this is the idea. So here we have a and here we have b, and we have chosen this particular point in such a way that this width and this width are same, and we are denoting that width by h. So now, so this coordinate will be a plus h and this will be a plus 2h. So we have a plus 2h is equals to b, and from this we can find out that h is, the width is b minus a by 2. Here a and b are fixed, mind you, a and b are fixed. All right. Now to find out the area, so let us say this area, so this area is a1, the area of this rectangle, and the area of this particular rectangle is a2. All right. So a1 will be this base, which is h, and this particular height, which is simply f of a. All right. And the area of this particular rectangle a2 will be the base, which is h, multiplied by the height. So this height is f of a plus h. All right, so this point is f of a plus h. Since this point is a plus h, this will be f of a plus h. All right, so now, so this is the area of the first rectangle and this is the area of second rectangle. So when we sum them up, we get this area plus this area, which will be somewhat, I mean, like nearer to the actual area that we have. So this a1, whatever a1 we have, this a1 will be actually less than the area we want. So the area under this curve will be integral a to b f of x dx. This a1 will be, a1 is this area, a1 will be less than this integral. Why is it less than this integral? Because when we compute a1 plus a2, we are ignoring this particular blue portion. This blue portion also lies under this curve, but that is not taken into consideration while calculating a1. Therefore, a1 is less than the actual area. This is the actual area. Now, let us compute the area in a different way. All right. So we have same a and b. Here you have a and here you have b. This width is h and this width is also h. All right. So now instead of making rectangle inside the curve, under the curve, so we can make the rectangle like this. The first rectangle looks something like this and the second rectangle looks something like this. All right. So now instead of finding the area under this curve, I mean under this particular curve, what we do is we find the area of this particular rectangle and we find the area of this particular rectangle and then we sum them up. So let us say this is a1 and this is a2. We find a1, we find a2 and then we sum them up. All right. So here this is a, this is a plus h, this is a plus 2h, but a plus 2h is b. So from here we can find out the width is still the same, b minus a upon 2. So now what will be your a2? a2 will be this width, which is h, times this length. This length is, this is a plus h, this point is a plus h, so this will be f of a plus h. So I have written here. So this is the first area. Now we have to compute the area of this particular rectangle. So that will be this width, which is h, multiplied by this particular length. This particular length is simply f of b, f of b. But b is same as a plus 2h. So that is f of a plus 2h. So this is a2. Now this a2 will be greater than the actual area because the actual area is just this part. And while computing a2, we are including this blue portion also. So this is the extra portion that got added while computing a2. All right. So this is a1, this is a2. So this actual area lies between a1 and a2. Okay. Now, what happens? So this is a, this is b. Till now we made only two triangles. What happens when we make three triangles? Okay. So we are going to explore that case in the next page. All right. So here you have, so here your a and b are fixed. So instead of making two rectangles, now I made three rectangles and the width of each rectangle is same, which is denoted by h. All right. Now the idea is the same. You compute the area of this particular rectangle, area of this rectangle, area of this rectangle, and then add them up to get the area under this curve. So a plus 3h is b, b minus a upon 3 is h. So now your a1 will be area of first rectangle, which is h times f of a, second rectangle h times f of a plus h, area of third rectangle h times f of a plus 2h. So that is what is written here. Similarly, instead of finding the area this way, let us find out the area this way. Let us make the rectangles like this. All right. Instead of making the rectangles under the curve, let us make the rectangles above the curve. All right. So here also this part is understood. So now area of this particular rectangle is this h times this length f of a plus h, and next rectangle's area is h times f of a plus 2h. This is f of a plus 3h. All right, so this is a1, this is a2. I mean, like, your a1 is lesser than the actual area, because this we are not including blue area in the calculation, and your a2 is greater than the actual area. So actual area is just this much, and this blue area is the extra thing that got added while computing a2. So your actual area lies between a1 and a2. So now this particular a1, when you have considered 3 rectangles, and this particular a1 when you consider only 2 rectangles, what is the relationship between those two a1s? So when you have considered 2 rectangles and when you have considered 3 rectangles, all right, so this is the case where you have considered 2 rectangles and 3 rectangles. Here you got one a1 and here you got one a1. So this particular a1, when you have considered 3 rectangles, is greater than this a1, and this a1 is nearer to this actual area, because this blue area you see here, so we are leaving out lot of area here. So this is like lot of area. So when you have 3 such rectangles, so this area which is getting left out in the computation, it got smaller. I mean, the area is minimized. So like we are nearer to the actual area when we consider 3 rectangles instead of 2 rectangles. So now let us say we have considered 4 such rectangles. In that case, so our area will still get nearer to the actual area. When you have 5 rectangles, the computation of area will be still closer to the actual area. So let us say we have n rectangles, and let us say this n is a very large number. So then your 2 lines that you have, the rectangles that, I mean, like the 2 lines that form a single rectangle, so lies very close to each other. All right, very close to each other. So this will be f of a. All right, so I'll write it up. So this point will be f of a, and this point will be f of a plus h. All right, now when n gets really large, when n is very huge, okay, when n tends to infinity, let us say, so we have h is equal to b minus a by n. All right, so in the case when we have 3 rectangles, h is b minus a by 3. When we have 2 rectangles, h is b minus a by 2. When we have n rectangles, h will be b minus a by n. All right, so now when n tends to infinity, this h tends to 0, and h is what? H is the width, this width. All right, when this h tends to infinity, f of a, all right, f of a will be nearly equal to f of a plus h, almost equal. These two are almost equal. So when f of a and f of a plus h are almost equal, let us say in this case, so initially when we have 3 rectangles, this much of area, this blue area is getting left out. When this comes here, this blue area gets reduced. Now it is this much only. When this comes here, the blue area still gets reduced. When it comes so close, this blue area will be negligible. So the computation of area gets close to the actual value of area when we increase the value of n. So let us say there are n rectangles. So in the first case, a1 is a plus, when we have 3 rectangles, a1 is like f of a plus f of a plus h plus f of a plus 2h. So we went till 2. When we have 1 rectangle, I mean 2 rectangles, it is f of a plus h. Here it is f of a plus 2h when we have 3 rectangles. So when we have n rectangles, it will be f of a plus h, a plus 2h, and so on, a plus n minus 1h. Okay. Now let us see what a2 is. When we have 2 rectangles, f of a2, I mean a2 is f of a plus h plus f of a plus 2h. When we have 3 rectangles, a2 is a plus h, a plus 2h, a plus 3h. When we have 3 rectangles, we went till 3. When we have 2 rectangles, we went till 2. All right. So when we have n rectangles, f of a2 is a plus h, a plus 2h will go till n, f of a plus nh. Now here also this a1 less than the actual integral, there should be a dx here, less than a2. Alright. So this is when we have n rectangles. Alright. So now when the n is very large, this blue area gets diminished. I mean this blue area gets so small, negligibly small, that whatever you compute with a1 or a2 will be almost equal to your actual area. Alright. Now I have just written down a1 in case of n rectangles. So now here this is simply a plus 0h. This is a plus 1h, this is a plus 2h, this is a plus n minus 1h. So we can write this whole thing as a summation. R runs from 0 to n minus 1. A is a plus rh. Alright. You put r is equal to 0, you'll get this term. You put r is equal to 1, you'll get this term. You put r is equal to n minus 1, you will get this particular term. So this is the sigma representation of a1. Alright. Now what is the sigma representation of a2? So this is the formula for a2. Okay. We saw it in the previous slide. Alright. Now, so this starts from a plus h, a plus 2h, and it goes till a plus nh. So this can be written as a plus rh, r running from 1 to n. You put r is equal to 1, you'll get the first term. Put r is equal to 2, you'll get the second term. Put r is equal to n, you'll get the last term. So this is the sigma representation of a2. So now we have this a1 and a2. Alright, and this is the relation that we have. When n tends to infinity, h is b minus a upon n. Alright, so when this n goes to infinite, h goes to 0. Alright. In that case, when h goes to 0, what does that mean? When h goes to 0, what does that mean? So your lines are so close. This distance is nothing. There is no distance here. So like the distance between two lines, it is 0. So it is as good as computing the entire area under the curve. Alright. So when n goes to 0, your a1, a2 and this integral, everything becomes the same value. Alright. They all tend to the same value. So n tends to infinite gives you the limiting values of a1 and a2, and those limiting values will be equal to the actual area. Alright. Now this is the actual area. Now this actual area is equals to a2 when n tends to infinite. Correct. Now let us substitute what a2 is. So a2 is h times r is equals to 1 to n f of a plus rh. So I have substituted the same thing here. Alright. Now h is b minus a upon n. So I have substituted b minus a upon n, b minus a upon n. Alright. Now, so this is the formula. So here you have a summation and you have to compute the limit of that summation when n tends to infinity. So to compute this kind of limit, we don't have to actually compute the limit, but if we find this particular integral, it is as good as finding the value of this particular limit. Alright. So this sigma, whatever we have here, so we have converted this sigma, limit of this sigma, into this particular integral. This is exactly what I was talking at the beginning of the video. So now let us look at some special cases. So when your a is 0, so that is when your lower bound of the integral is 0. That is when this is 0. When your a is 0, so this will become b upon n. So this is b upon n, and this goes to 0. So this goes to 0. So this will be simply br upon n. Alright. This is when a is equal to 0. So now, so this is what we got when a is equal to 0. So let us explore one more special case of this particular result. So when your b is 1, so this b is 1, so this will become 1 upon n and this will become r upon n. This is a very important result. I mean, these two results are very, very important. So these are very frequently used in your JEE advanced exam, and you can expect questions from this topic every year on your JEE exam. So to understand this concept clearly, to explore how we can apply this concept in solving questions, let us solve this particular question. All right, so this is a very fundamental application of this particular concept. So let us solve this question. So you have this particular limit which you have to evaluate, and the limit is given by limit n tends to infinite n factorial by n to the power n whole power 1 upon n. So this is the limit that you have to evaluate. All right, so now if you compare this particular limit with this limit, you don't have any summation in this limit. All right, so this limit does not look anything like the result that we have derived. All right, so let us see what we can do about it. Let us see how to convert this particular limit into this particular format. All right, okay, let us go ahead. So this is L. So let us apply logarithm to this limit on both sides. So that will be log L is equals to limit n tends to infinite n fact. So this will be log of n factorial by n to the power n whole power 1 upon n. And now there is this result in logarithms. So if you have log a to the power b, that is simply b times log a. So here this is your a and this power is your b. All right, so log L is simply limit n tends to infinite. This is in the form log a to the power b. So that is simply b times log a. Your b is 1 by n times log n factorial by n to the power n. All right, now even now this particular limit does not look anything like the result we have derived. Here we have summation, here still we do not have any summation. So let us see what we can do about it. Okay, all right, let us proceed. So now you have limit n tends to infinite 1 upon n log, what is n factorial? N factorial is 1 times 2 times 3 times and so on times n upon n to the power n is n into n into n into n. All right, so here you have n terms, n got repeated n times, and here also in the numerator you have n terms 1 to n. So this can be written as, so limit n tends to infinite 1 upon n log 1 by n times 2 by n times 3 by n and so on times n upon n. All right, now again there is a result in limit logarithms. So you have log a1 times a2 times a3 and so on an is equals to log of a1. So here you have product of these numbers. When you apply logarithm to the product of the numbers, so you'll get log a1 plus log a2 plus and so on log an. All right, so this can be written as limit n tends to infinite 1 upon n log of 1 by n plus log 2 by n, this is log a2, plus log 3 by n plus and so on log n by n. All right, now this can be written as again limit n tends to infinite 1 by n times sigma r is equal to 1 to n log of r upon n. So you substitute r is equal to 1 in this sigma, you'll get the first term. Put r is equal to 2, you'll get the second term. And similarly put r is equal to n, you'll get the last term. So this whole bracket can be replaced by this particular sigma notation. All right. Now, if you compare this particular result we have and this thing, so let's see, you have limit n tends to infinite here, similar thing here, 1 upon n, 1 upon n, sigma r runs from 1 to n, sigma r runs from 1 to n, f of r upon n. So now let us say f of x is equal to log x. Then what is f of r upon n? So that will be log of r upon n. Okay. So your f of x is log x and your f of r upon n, which is log r upon n, sits here. All right. Now this particular thing looks exactly like this result that we have derived. So now to compute this particular limit, we just have to compute this particular integral. Let us do that. So what is the integral? Integral 0 to 1 f of x. F of x is log x dx. So this will be log L. So this is logarithm of L. So this is log L. All right. This is log L. So now we have to compute this particular integral. Let us do that. Log L is equals to integral 0 to 1 log x dx. So this log x dx can be written as 1 times log x dx. And now we can use integral by parts. So this is your first function u, and your second function will be v is equal to integral 1 dx. That is x. Your second function is x. So now the integral will be u times v limits 0 to 1 minus integral v x du. Du is u is log x, du will be 1 by x dx, 0 to 1. When you put x is equal to 1, log x will become 0. When you put x is equal to 0, x will become 0. So this whole term is 0. So that will be minus integral 0 to 1 dx. So that will be minus integral 1 dx is simply x from 0 to 1. So this is simply minus 1. So log L is minus 1. So the base of the logarithm here is e. So L will be e to the power minus 1, that is equal to 1 by e. So the value of the limit L is simply 1 upon e. See how beautifully we have converted the limit into this particular format and then solved it. So here you have the simple looking limit. We have expanded the limit, applied few properties of logarithms, all right, and then beautifully we have converted this particular product into this particular summation, giving us a representation like this. And then we figured out what the function f of x is by comparing this particular thing we have and this particular representation of the limit that we have achieved. All right, we have found out log f of x, and then all we had to do was find out integral 0 to 1 fx dx. Right, we have just done that. So log L is integral 0 to 1 fx dx. So here we have used integration by parts to compute the value of the integral and eventually finding the value of the limit. So if you like this content, give this video a thumbs up, share it with your friends, and subscribe the channel for more such content. And do comment if you have some queries regarding this concept, and follow the playlist. So I'll be solving more of this, more questions on this particular concept in the subsequent videos. Thank you.